Hi friends, welcome to Obhi's Math e-Pathshala. Today's topic is Topological Vector Space, Lecture 1. If you like this video, please share and subscribe to your friends. Thank you.
So we are going to have two notions. One is vector space and another one is topological space. And now we are going to blend them together and we will have a notion of topological vector space. But what is the definition of topological vector space? So let me start with very preliminary concept of topological group, which will lead to the particular example of a topological group, which is going to be topological vector space. So topological group. So what does it mean? So we first consider an abelian group. Abelian group, and suppose we are denoting the composition of the group by plus. Since it is abelian, so we are going to define, we are going to denote the composition by plus. And yeah, then uh, if we induce a topology on G for which the algebraic operations algebraic operations uh, will be compatible with the topology. Defined. That means, that is, what does it mean by compatibility? That is, first one is continuity of the operation. That is, continuity of addition holds. That is the structure that we have already induced on the set G. It will be continuous with respect to the topology defined on G. That is the map uh, x, y to x plus y. So which is a map from G cross G to G. Okay. Where in G cross G we are considering the product topology. Product topology. Okay. So this map will be continuous with respect to the topology defined on G. And also continuity of inversion. Continuity of inversion. That means the map which sends x to minus x, which is a map from G to G, it is also continuous. Okay. So, so on an abelian group, we would like to define a topology with respect to which both these maps will be continuous. Okay. Then G is defined to be a topological group. That is, you consider an abelian group, additive abelian group, on which you are going to define a topology for which the inversion and the operation addition, these are continuous with respect to the topology defined on G. Okay. So, uh, so that is precisely speaking, we can say that the topology on G is a topology compatible with the group structure. So we are going to blend the algebraic structure with a topological structure. Okay. So in this way, we can define a topological group on an abelian group G. Okay. Now axiom 1. What does it tell? So it tells you that uh, the map xy to x plus y, a map from G cross G to G, it is a continuous map. From G cross G to G, right? That means, so that means for any neighborhood W of x plus y, right? So you are going to consider any neighborhood around x plus y. Then there exist neighborhoods around x and around y. So there exist neighborhoods u around x and v around y, such that u plus v will be a subset of ux plus vy is a subset of wx plus y. Okay. So axiom 1 tells you this fact, that given any neighborhood around x plus y, you are going to have two neighborhoods, one around x and another one around y, such that their sum will be a subset of wx plus y. And axiom 2 tells you that. So what is the axiom? That is the map which sends x to minus x. That is a map from G to G. It is a continuous map. Continuous map. So that means for any neighborhood W of around minus x, you are going to have a neighborhood V around x, such that such that uh, minus of Vx will be a subset of W minus x, right? Okay. 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 Now, remark is that uh, instead of taking axiom 1 and 2, can we replace it with exactly one axiom? Yes, because of the fact that, so recall that when do you call a subset of G a subgroup, that is H is a subgroup if and only if for every xy belongs to H, x minus y, x minus y belongs to H, right? So keeping in mind this condition of a subset of G to be a subgroup, we can replace this axiom 1 and 2 by means of this one, that is we can just write down a statement, uh, axiom 3, which is the map which sends xy to x minus y, that is from G cross G to G, is a continuous map, is a continuous map. Okay, I'm just going to write the statement of the axiom. Now can we show that axiom 3 implies axiom 1 and axiom 2 both? Okay, can axiom 3 can be replaced in the for axiom 1 and 2? Hmm? The answer is yes. Why? Because you just consider, uh, firstly, consider the additive inverse, additive identity. Consider the additive identity, which is denoted by 0. Okay, then you are going to have this map, that is 0 comma y. Okay, which sends to 0 minus y. Okay, and it is a continuous map, right, by the axiom 3. Now, since you fix up this point, then it is a map from G to G, right? So that means it is a map which sends y to minus y, and this is true for all y belongs to G. So it is a continuous map. That means axiom 2 holds, right? Okay, okay, and then taking axiom 3 and axiom 2 together, you are going to have, so taking axiom 3 and axiom 2. This will imply axiom 1, right? So here you can write that axiom 2 holds. Okay. So that means axiom 3 will imply axiom 1 and 2 both. And now what about the converse part? It is obvious that if axiom 1 and 2 will be satisfied by the topology induced on G plus, then it will satisfy axiom 3, obviously. And obviously, axiom 1 and 2 both will imply axiom 3. Okay, right? Okay, okay. So you can replace axiom 1 and 2 by axiom 3 in certain cases. Okay. Okay. Now let us have a look on some examples. That is, the first one will be any abelian group will going to be a topological group with respect to the discrete topology. So any abelian group with respect to discrete topology will be a topological group. Okay, because you can check the continuity conditions and it will hold very nicely. Okay, and these examples will give you some, will be used as counter examples in many cases. Okay, number 2, suppose you are having the additive groups. Okay, so these are abelian groups with respect to addition, and with respect to their, so these are all so these are all topological groups with respect to usual topologies. That can be defined on R C. Okay. R C.
আচ্ছা স্যার,
Hmm.
আমি বলছি টোপোলজিক্যাল গ্রুপটা ওটা কি স্ট্রং রেজাল্ট আমরা যে নর্মাল যে গ্রুপটা পড়েছি, মানে এটা জেনারেলাইজেশন গ্রুপের?
না, টপোলজি এখানে মূল ব্যাপারটা হচ্ছে যে প্রথমে যেটা বললাম যে তুমি প্রথমে আমি
এটা
অ্যাকচুয়ালি
দুটো
টপোলজি,
স্ট্রাকচার সেটা টোপোলজি একটা অ্যালজেব্রিক।
হ্যাঁ অ্যাকচুয়ালি ব্যাপারটা হচ্ছে যে আমার উদ্দেশ্যটা হচ্ছে যে আমি দুটো কনসেপ্টকে মিক্স আপ করতে চাইছি এবং সেটার মাধ্যমে আমি দেখতে চাইছি যে আরো কি কি রেজাল্ট আমি জেনারেলাইজ করতে পারি। হ্যাঁ, যেগুলো আমাদের এই আর সি এই সমস্ত গ্রুপে যে হয়, হ্যাঁ তাদের থেকে আরো জেনারেল কি জায়গায় আমি যেতে পারি এবং সেগুলোকে কিভাবে ডিফাইন করা যেতে পারে, হুম, ইন টার্মস অফ অ্যালজেব্রা অ্যান্ড algebraic structure and topological structure. বুঝতে পেরেছো? তুমি অলরেডি যখন আমরা আর আর সিতে করেছি, তুমি দেখো এটা খেয়াল করো যে আমরা এটা তো করেছি যে অ্যাডিশনটা হচ্ছে কন্টিনিউয়াস ফাংশন। কারণ হচ্ছে প্রথমেই আমরা দেখো
আচ্ছা,
করেছি যে এক্স এন একটা সিকোয়েন্স, ওয়াই এন একটা সিকোয়েন্স, এক্স এন যদি এক্স এ কনভার্জ করে, ওয়াই এন যদি ওয়াই এ কনভার্জ করে, then xn plus yn will converge to x plus y. So that means the addition is continuous. Similarly, তুমি যদি একটা নন জিরো স্কেলার নাও, তুমি দেখতে হবে যে যে কোনো একটা তুমি ধরো, বা তুমি ধরো এক্স এন একটা সিকোয়েন্স দিলে যেটা এক্স জিরোতে কনভার্ট করে, তাহলে মাইনাস এক্স এনটা মাইনাস এক্স জিরোতে কনভার্ট করবে। ঠিক আছে? কারণ এই যে বেসিক যে জায়গাগুলো, হ্যাঁ, তাহলে সেইখান থেকে তুমি এই আইডিয়াটাকে জেনারেট করলে যে তার মানে আমাকে এমন একটা টপোলজি ডিফাইন করতে হবে যেখানে এই দুটো ম্যাপ হচ্ছে কন্টিনিউয়াস জেনারেলি। ঠিক আছে না?
স্যার আমি বুঝতে পারছি, কিন্তু স্যার আমার কোশ্চেনটা হচ্ছে, স্যার বলছি আমরা যখন গ্রুপ করেছি অ্যালজেব্রিক স্ট্রাকচার,
হ্যাঁ,
আর যখন স্যার এটা একসাথে পড়ছি মিক্স আপ করে, মানে টোপোলজিক্যাল গ্রুপটা যেটা, আমি স্যার এটা কি, এটার থেকে বেনিফিটটা কোন জায়গাটাতে, মানে রেজাল্টের দিক থেকে?
হ্যাঁ, অবশ্যই। তুমি ধরো তুমি এখানে তুমি অনেক নতুন ধরনের, যেমন হচ্ছে তুমি এখানে আমরা বাউন্ডেডনেস ডিফাইন করব। আমি ধরো ইন জেনারেলি টোটালি বাউন্ডেডনেস ডিফাইন করব। আমি ইন জেনারেলি তোমার কি বলে
মানে স্যার টোপোলজির প্রপার্টি গুলো গ্রুপের উপর আমরা অ্যাপ্লাই করবো, তাই তো?
হ্যাঁ, একদম
আচ্ছা,
অবশ্যই।
বুঝতে পেরেছি।
হ্যাঁ,
আর একটা
অবশ্যই।
সুন্দর রেজাল্ট আসতে পারে এরকম করে। আচ্ছা।
হ্যাঁ, নিশ্চয়ই
হ্যাঁ, হ্যাঁ,
আসবে
হ্যাঁ,
তো
বুঝতে
বটে।
পেরেছি। হ্যাঁ, হ্যাঁ।
তোকে মিক্স আপ করছো, নিশ্চয়ই আসবে। যেমন হচ্ছে তার মানে ইন জেনারেলি, তার মানে অ্যাকচুয়ালি তুমি যদি ভালো করে লক্ষ্য করো এই এক্সাম্পল গুলো, তার মানে অ্যাকচুয়ালি এরা হচ্ছে তোমার ওই যে কোনো একটা নন লিনিয়ার স্পেস যদি নাও, হুম, যে এনি নন লিনিয়ার স্পেস, নন লিনিয়ার স্পেস, so any non-linear space, so it is in particular an additive group, hmm, এবং and since you have defined a norm on that space, so it is a topological space, hmm? And not only that, in any non-linear space is a topological group. Why topological group? Because if you take uh, now you need to check the continuity of addition and the continuity of inversion. Okay, so 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 if limit of xn will be x naught, limit of yn will be y naught, then what you will have, norm of xn plus yn minus x naught plus y naught, it will be norm of xn minus x naught plus yn minus y naught, which will be less than or equal to norm of xn minus x naught plus norm of yn minus y naught. So using triangle inequality, you will see that this will be tending to 0 as n approaches infinity, right? So that means limit of xn plus yn will be x naught plus y naught. So this proves that the addition is, so this implies plus is continuous, right? And in a similar way, you can check that now since norm of x is equal to norm of minus x, right? So using this fact, you can easily prove that. So the inverse, the inversion, the inversion is continuous. Just take one sequence for if limit of xn equal to x naught, then norm of minus xn minus of minus x naught equal to norm of minus xn plus x naught, and so it is xn minus x naught. So it tends to 0 as n approaches infinity. Okay. So any nonlinear space is a topological group. Okay. 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 Example 4. Suppose you are considering the non-zero set of all non-zero reals and non-zero complex numbers, and they will form a group with respect to multiplication. Okay. And then you will see that these groups are topological groups. These groups are topological groups with respect to the usual topology defined on respective spaces, respective groups. Okay, this is very easy to show. Okay, now we need to uh, have an example which will not going to be a topological group. That is one example which is not a topological group. Okay, which is not a topological group. Now we will see, we can construct an example by proving a property of topological group, which is a topological group will be a regular space. Will be a regular space. What does it mean by a regular space? That is, which means that for any neighborhood W of a point X, suppose it is Z, belongs to G, there exists a neighborhood V of X such that V closure will be a subset of W. Okay. So to construct an example which is not going to be a topological group, you need to consider this property of a topological group. So we need to construct a group and induce a topology on that group which is going to be non-regular topology. Okay, non-regular topology. So an example at your hand is the example of a non-regular topology will be, suppose G be an infinite group, infinite additive group. Okay, where we define co-finite topology. Okay, co-finite topology. Now, what does it mean by co-finite topology? Where the open sets are either empty, or if it is non-empty, then its complement will be finite. Right? That is a set is open if and only if either it is empty, or if it is non-empty, then its complement will be finite. So in a cofinite topological space, the closure of any neighborhood will be the whole space. Okay, closure of any neighborhood will be the whole space. Okay, suppose you consider, so okay, then we see that for a neighborhood uh, V sorry, W of x, W of x its closure W bar. Now what is W bar? What is W bar? The closure of any set is a closed set, right? Closed set. So, so that means yeah. So that means yeah. So this is a closed set in G. Okay, this is a closed set in G. Now what does it mean? Now what are the closed sets of a cofinite space? These are the closed sets are either it is phi and any finite subsets of G, right? Okay. Any finite subsets of G. Now, how many? What is the cardinality of this W bar? Now, what is the cardinality of W bar. What will be the cardinality of W bar? Any finite subsets phi, any finite subset of G, and the whole set.
স্যার ওইখানে ফাইটা না লিখলেও তো চলতো।
হ্যাঁ,
ফাইটাকেও তো স্যার আমরা ফাইনাইট সেট হিসেবে ধরে নিই।
ফাইটাকে
ফাইটাকেও তো স্যার আমরা ফাইনাইট সাবসেটই ধরি।
মানে আমি নন এমটি বলতে চাইছি, মানে একটা হচ্ছে এমটি সেট, আর যদি নন এমটি হয় এনি ফাইনাইট সাবসেটস। হ্যাঁ, তুই ফাইটাকেও নিয়ে নিতে পারো, অসুবিধা নেই, প্রবলেম নেই। মানে স্পেসিফিক্যালি বললাম আর কি। এবার হোয়াট ইজ দ্য কার্ডিনালিটি অফ ডব্লিউ?
স্যার ফাইনাইটই হচ্ছে, আর না হলে ফুল এক্সট্রা হয়ে যাবে।
হ্যাঁ, এবার ধরো নাও নোট দ্যাট W is contained in W bar. So you have to choose one W, a neighborhood W of X, which has infinitely many elements. So we need to choose one neighborhood W of X which will have infinitely many elements. এটা কি সম্ভব? পসিবল? ইজ ইট পসিবল?
হ্যাঁ স্যার ওরকমই তো হচ্ছে।
কিভাবে বলো? এবারে গ্রুপটা কিন্তু ইনফাইনাইট গ্রুপ নিয়েছি।
হ্যাঁ স্যার।
Particularly, just take an infinite group. So suppose it is Z plus. Then so what would be a possible neighborhood of X? Just take, the idea is that since it is infinite, so you can choose 2 points. Suppose one is X, another one is Y, where X not equal to Y, right? Then singleton Y is a closed set, right? And this implies X belongs to capital Z minus singleton Y, which is an open set, right? Which is an open set. So you can choose, now since it is an open set, so it is a neighborhood of X. So you can choose W as Z minus singleton Y. Then this W will contain infinitely many elements, and this implies W bar will be the whole group Z, right? Okay, because as W is contained in W bar. So being an infinite subset of Z, and since we have defined cofinite topology on Z, so W bar must be whole of Z, being an infinite set, right? So W bar will be Z. So this means that, so this is a non-regular topology, topological space, right? Non-regular topological space. So in this way you can construct examples of not being a topological group. Okay. Now let G be a topological group. Okay. Then we can define two maps immediately. One is, suppose TA from G to G defined by TA of x goes to x plus a for all x belongs to G, which is called translation map. And another one is M minus, okay, which is from G to G defined by M minus 1 of x is minus x, and it is called inversion, right? And these maps, so the theorem is that these TA and M minus, so these are homeomorphisms. Homeomorphisms of G onto G for every A belongs to G. Okay. So why it is so? What will be the proof? এটা তোমরা এটা নিজেরা করো। এটা হোমিওমরফিজম দেখো। হোমিওমরফিজম মানে কি? What do you mean by a homeomorphism? That is, the maps are continuous, these are bijections, and their inverse maps are also continuous. দেখো তো এটা চেক করে। পাচ্ছ? হোমিওমরফিজম দেখাতে হবে।
হ্যাঁ স্যার হয়ে যাচ্ছে।
হচ্ছে না? ইজিলি একদম।
স্যার
কি করে দেখাবে?
কিন্তু স্যার 1 1 1 2টা তো অন টুটা হয়ে যাচ্ছে,
হুম,
আর ইনভার্স ফাংশনটা তো টি অফ মাইনাসে হয়ে যাচ্ছে।
হ্যাঁ একদম।
তাহলে
তার
তো
মানে
স্যার ওটা যেহেতু
হ্যাঁ, যেমন ওরা যেহেতু কন্টিনিউয়াস, অতএব এটাও কন্টিনিউয়াস হবে, সেম টাইপের ম্যাপ।
হুম, আর m-1 এর ইনভার্স তো নিজেই হয়ে যাচ্ছে।
হ্যাঁ 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 একদম। তো now since T of A compose T of minus A, so that means T of A of, so it is x plus minus A, and that means it is x plus minus A plus A, so that means it is x. So for all x belongs to G, so that means TA inverse is T minus A, and for m minus 1, so of x, so therefore it is m minus 1 of minus x, that means it is x for all x belongs to G, that is m minus 1 inverse is m minus 1, right? So therefore by axiom 2, m minus 1 is continuous, and also by axiom 1, for any neighborhood w of x plus a, there exist neighborhoods u of x and v of a, so that ux plus va will be a subset of w, it is x plus a, right? So therefore, so this implies so this implies uh, this implies ux uh, equals to ux plus a, right? Now what is ux plus a? It will be contained in ux plus va, since va is a neighborhood containing a, around a, So ux plus a is a subset of ux plus ba, and now it is a subset of w x plus a. So this proves that TA is continuous, right? Okay. So this completes the proof, and we have shown that translation map and the inversion map, these are all homeomorphisms of G onto G. Now we would like to uh, define another concept which is of uh, homogeneous space. What does it mean by a homogeneous space? So a topological space is going to be homogeneous. A topological space, suppose X, is defined to be homogeneous if for any two points x, y of capital X, there exists a homeomorphism. There exists a homeomorphism of X onto itself. There exists a homeomorphism, suppose capital F, of X onto itself, such that capital F maps the point X to Y. Okay. So for any two given points X and Y, there will be a homeomorphism F of X onto itself, such that the map will send x to small y. Okay. Now in this context you will see that, so now suppose capital G be a topological group. Okay. And let x and y be any two points of G. Okay. Now define a map T from G to G by T of T of uh, T of W goes to W minus X plus Y. Okay. So that means this is true for all W belongs to G. That means it is actually minus of uh, X minus Y, right? Or you can see this map as W plus Y minus X, whatever it is. So that means it is actually a translation map. And for being a translation map, it will be a, so it is a homeomorphism of G onto itself. Not only that, and also see that what is T of X? Now what is T of X? That is X minus X plus Y. So that means it is Y. So this proves that theorem any topological group is homogeneous. Okay. Okay. So remark is that, so since any topological group is homogeneous, so that means, so so the homogeneity of topological groups speaks of the fact that it is enough, it suffices to investigate the local properties of the local sorry properties of the groups at just one point, right? Because you have defined, you can define any, you can define a homeomorphism from G to G, from G1 to G, which sends any point to another. So that means you can always transfer the set of all neighborhoods around any point to the set of all neighborhoods around another point. So whenever you are considering the local properties, you can check, you can investigate those properties at just one point. And in particularly, we are considering the additive identity. That is, we will check the properties around the additive identity 0. Okay. So you shall consider the set of all neighborhoods around 0 only. We don't need to consider the neighborhoods around each point because of this homogeneity. Because you can transfer the set of neighborhood systems at each point to the neighborhood system at the additive identity. Okay. And they will coincide actually. For example, uh, if you can find out uh, a compact neighborhood around 0, then you can conclude that G is locally compact, because around 0, for every neighborhood you can find out one compact neighborhood around 0. So that means it is locally compact at 0. So you can conclude that G is locally compact. The whole space is locally compact. Okay. So in this way you can check any local properties of G around just one point, which is the additive identity 0. Okay. Okay.
কম্প্যাক্ট নেবারহুড জিনিসটা কি?
কম্প্যাক্ট নেবারহুড মানে হচ্ছে যে তুমি ধরো যে কোনো একটা নেবারহুড নিলে, একটা সেম সেট কম্প্যাক্ট মানে এটা কি?
প্রত্যেকটা ওপেন কভারের ফাইনাইট সাব কভার।
মানে এটা এখানেও তাই, যে তুমি একটা নেবারহুড পাচ্ছ যেটা কম্প্যাক্ট। ঠিক আছে? তুমি একটা নেবারহুড
ওই
পাচ্ছ,
নেবারহুডের আচ্ছা করসপন্ডেন্স আরেকটা নেবারহুড পাবো যেটা ওই ফাইনাইট সাব কভার থাকবে।
তুমি একটা নেবারহুড নিলে, যে কোনো একটা পয়েন্টে অ্যারাউন্ডে একটা নেবারহুড নিয়েছো যে কোনো একটা, তার মধ্যে আরেকটা নেবারহুড তুমি পাচ্ছ, যে নেবারহুডটা তোমার মানে যার ক্লোজারটা তোমার কম্প্যাক্ট, মানে লোকালি কম্প্যাক্টের ডেফিনেশন হচ্ছে এটা। ঠিক আছে? মানে তুমি একটা অ্যারাউন্ডে একটা নেবারহুড নিলে, তুমি যে ধরো এক্স একটা পয়েন্ট, যে কোনো একটা নেবারহুড নিয়েছো এনএক্স, এনএক্স এর মধ্যে যদি তুমি একটা নেবারহুড পাও যার ক্লোজারটা কম্প্যাক্ট হয়ে যাচ্ছে, তখন তুমি ওটাকে বলতে পারো ইট ইজ লোকালি কম্প্যাক্ট অ্যাট স্মল এক্স। ঠিক আছে? টপোলজিক্যাল গ্রুপে যেটা মজাটা হচ্ছে যে তুমি শুধুমাত্র একটা পয়েন্টে যদি দেখাতে পারো, তাহলেই ব্যাপারটা সব জায়গাতেই সত্যি। বুঝতে পারলে? মানে জাস্ট চেক এনি প্রপার্টি, লোকাল প্রপার্টিস অ্যারাউন্ড ওয়ান পয়েন্ট। ইন পার্টিকুলারলি উই আর টেকিং the additive identity 0। তুমি জাস্ট জিরোতে কি হচ্ছে সেটা দেখবে, জিরোর অ্যারাউন্ডে তুমি কি হচ্ছে, তোমার লোকাল প্রপার্টি গুলো কি কি তুমি হোল্ড করছো। যদি হোল্ড করে, যে কটা হোল্ড করবে সবগুলো ওই গোটা স্পেসটাতে হোল্ড করছে। ঠিক আছে? তোমাকে আর বাকি পয়েন্টগুলোতে চেক করার দরকার নেই, বিকজ অফ হোমোজিনিটি, বিকজ টপোলজিক্যাল গ্রুপস আর হোমোজিনিয়াস। হ্যাঁ, যে তুমি যে কোনো সিস্টেমটাকে তুমি তুমি ধরো জিরোর অ্যারাউন্ডে যা হচ্ছে সেই গোটা জিনিসটাকে তুমি যে কোনো পয়েন্টে নিয়ে যেতে পারো ইন টার্মস অফ দিস ট্রান্সলেশন ম্যাপস, দিস হোমিওমরফিজম। হোমিওমরফিজম মানে কি? এখানে যা হচ্ছে ওখানেও তাই হবে। হোমিওমরফিজমের কনসেপ্টটা তো তাই, টপোলজিক্যাল যা যা প্রপার্টি তুমি পাচ্ছ সেগুলো এখানে যদি হয় ওখানেও হবে, তাই না? তো টপোলজিক্যাল গ্রুপে এটা মানে বেসিক একটা, মানে এটা ইন্টারেস্টিং একটা ফিচার আর কি, যে ইট ইজ হোমোজিনিয়াস। হ্যাঁ, ওকে। Okay. Another one, another nice consequence of homogeneity, which I have already told, homogeneity of a topological group is the following: is the theorem that is if let G be a topological group, sorry, let G be a topological group, okay, then uh, if curly B be a local base at 0, if curly B be a local base at 0, then you will see that the sets of the form, the sets of the form x naught plus b, the sets of the form x naught plus b, where b is sitting inside curly b, then the sets of the form x naught plus b will form a local base at x naught. Okay. So if curly B be any local base at 0, where x naught belongs to G, be any point. So if curly B be a local base at 0, then you will see that if you just translate those neighborhoods to x naught, that is x naught plus b, then they will form a local base around x naught. Okay, and it is the converse is also true. That means if you consider any local base around x naught, then it just translate those neighborhoods to 0 by means of the map minus x naught plus b, where b is sitting inside the local base around x naught. Then they will form a local base at 0. Right? Now, what does it mean by a local base? Local base means that if it is x, so for any neighborhood in x, you will find out one bx. The bx will be in a family of neighborhoods that is a subset of nx, where nx is the set of all neighborhoods of x. So any subfamily of nx will be defined to be a local base at x if for each neighborhood in x there exists a neighborhood bx which is in curly b. Okay, such that it is like that. Sorry, such that bx is a subset of nx. This is bx. Yeah, and this is curly bx. Yes. So a subfamily curly bx of the neighborhood system at x will be defined to be a local base at x if for each neighborhood at x there exists a member of that curly bx, capital Bx, that capital Bx is a subset of nx. Okay. Okay. So that means we need to show that. So what will be the proof? Left as an exercise. Okay. So as a consequence of this result of this, so okay, so as a consequence of this result, once we is that once we can be able to know the uh, neighborhood system at 0, then we will be uh, okay, so able to know the neighborhood system at 0, then we will be able to know the neighborhood system at each point, at each point small x belongs to G. Yeah. Okay. And not only that, not only that, uh, if if V be a neighborhood at 0, then x plus V be a neighborhood at small x for any small x belongs to G. And conversely, if W be a Wx be a neighborhood at x, then minus x plus Wx is a neighborhood at 0. Okay. Okay. Fine. Okay. Some so facts that in a topological group, G, for every neighborhood V of 0, there exists a neighborhood U of 0 such that U plus U will be a subset of V. Okay. So for any neighborhood V of 0, there exists a neighborhood U of 0 such that U plus U will be a subset of V. Now, how to prove this theorem, this fact? Just by considering
0 equal to 0 প্লাস 0 নিলে হবে?
exactly. So considering x and y both to be 0, then we see that the map which sends 0 comma 0 to 0 plus 0, which is 0, is a continuous map, right? And which means that for any neighborhood V of 0 around this 0, there exist neighborhoods, one is U1, another one is U2 of 0, both for both these zeros, this one and this one, such that U1 plus U2 is a subset of V. Okay. Now you know that intersection of two neighborhoods is again a neighborhood. So take U to be V1 intersection V2, which is a neighborhood at 0. Okay. Then U plus U. What is U plus U? Now U is a subset of V1 and this U is a subset of V2. So then V1 plus V2 is a subset of. So yes, this completes the proof of this fact. Okay. And not only that, the note is that if for any neighborhood V of 0, there exists a neighborhood u of 0 such that u plus u up to n times is a subset of V. That is, if we denote this addition by nu, then it is a subset of V, right? So for any neighborhood V of 0, there exists a neighborhood u of 0 such that nu is a subset of V. Okay. Now I would like to stop with by defining another important concept, which is symmetric sets in a topological group. Symmetric sets. So let G be a topological group. Then a subset A of G is said to be a symmetric set. Is said to be a symmetric set if X belongs to A if and only if minus X belongs to A. That is, A is equal to minus A. Okay. A is equal to minus A. Right. Okay. For example, suppose A be a subset of a topological group G. Then at once you will have some symmetric sets like that. Then A union minus A intersection minus A minus A. These are all symmetric sets. Okay. These are all symmetric sets. Why? Just check one. Let E equal to A union minus A. Then minus X belongs to E implies minus X belongs to A or minus X belongs to minus A implies. So that means X. So if minus X belongs to A, then X belongs to minus A, or if you take this one, then X belongs to A. That is, X belongs to A union minus A. Okay. So X belongs to A union minus A, and if you take X belongs to A union minus A, then you can get the reverse implications. So that means E is symmetric. And in a similar way, you can, if you consider A intersection minus A, then this will be again a symmetric set. If A minus A, it is again a symmetric set. And also we see that uh, if A is symmetric, then its closure A bar is also symmetric. Why? If A is symmetric, then its closure A bar is also symmetric. Why? Since for minus x belongs to A bar implies, what does it mean? That is for any neighborhood n minus x, it will intersect A for all neighborhoods. Okay, right? So that means, so okay. Now what is n minus x? Now what is n minus x? Now let y belongs to n minus x intersection A, where n minus x will be like this one, that is, it is minus x plus v, where v is a neighborhood of 0, right? V is a neighborhood of 0. Okay, okay. So then uh, okay, yes. So then y belongs to n minus x, which is equal to minus x plus v, implies y is equal to minus x plus some h, where h belongs to v, right? That means, so what is minus y? It is x minus h. Okay. Now note that since uh, since v is a neighborhood of 0, then minus v is also a neighborhood of 0, right? And so minus h belongs to minus v, which will be written as w. Okay, so that means minus y is equal to x plus w. Okay, now again you see that y belongs to a, also y belongs to a implies minus y belongs to a, as a is symmetric. Okay, so that means minus y belongs to x plus w intersection a. Okay, okay. So yeah, fine. So so for any neighborhood wx of small x, we see that wx can be represented as x plus w, where w be a neighborhood of 0. Okay, and then wx intersection a will be not equal to 5 because of this reason. Okay, as because you just take uh, the reverse one, that is as because minus uh, as because, yes, so minus x minus w, okay, intersection a will be not equal to 5. Okay, and this proves that so x belongs to a bar, that is minus x belongs to a bar implies x belongs to a bar and vice versa. So this proves that a bar is also symmetric. So if A is symmetric, then its closure is also symmetric. So with this one, I would like to end.